This video talks about the symmetry of polar equations. Now, I know in algebra we tested for symmetry with respect to the x-axis, y-axis, and origin, and then we kind of never did anything with it. Well, that was because we had good graphing techniques for all those different types of equations. When graphing polar equations, our only option for graphing is plotting points. And this can be very laborious because when choosing our theta values, which is our independent variable, we have to choose angle measures all the way around the circle. So if we know that it's symmetric side to side or up and down, that can cut down our number of thetas substantially. Our first type of symmetry in polar coordinates is symmetry with respect to the polar axis. Remember that the polar axis coincides with the x-axis. So we see if the point r theta is on the graph, then the point r negative theta is also on the graph. So our test for this type of symmetry is to replace theta with negative theta. And then you're going to clean up the equation. If the equation remains unchanged, then the graph is symmetric with respect to the polar axis. And when I mean unchanged, it's that you get back to the original. The second type of symmetry is symmetry with respect to the line theta equals pi over 2. Remember, pi over 2 is straight up, so this is kind of the same as symmetric with respect to the y-axis. If the point r theta is on the graph, then the point negative r negative theta is also on the graph. Our test is to replace r with negative r and theta with negative theta. And then we're going to clean up the equation. If we get the original back, then the equation displays symmetry with respect to the line theta equals pi over 2. And lastly, we have symmetry with respect to the pole. The pole and the origin coincide, so this is that diagonal symmetry. If the point r theta is on the graph, then the point negative r theta is also on the graph. So our test is to replace r with negative r. We'll clean it up. If we get the original back, then the graph will display that diagonal symmetry with respect to the pole. Now, please note, this is really important here. If a polar equation passes a symmetry test, then we know for sure that the graph has that kind of symmetry. However, if a polar equation fails a symmetry test, then the graph may or may not have that kind of symmetry. We don't know for sure. It's inconclusive. So we can never say it doesn't have that type of symmetry for sure. So in our next couple examples, we're going to test an equation for these three types of symmetry. And if it fails one of the types, we're not going to say no, but instead we're going to say maybe. So let's determine whether the graph of each polar equation displays symmetry with respect to the polar axis, theta equals pi over 2, or the pole. In our first example, r is equal to 2 sine of 3 theta. I like to get set up the exact same way I do in algebra, where I just am going to make a table. Not only does this keep me organized, but it also lets my instructor know what I'm doing, because if there's just a bunch of yeses and maybes, I can't decipher which type of symmetry you're talking about, and as a result, I can't give you credit for that. Okay, so here's my little table. For polar axis, the test is to replace theta with negative theta. For theta equals pi over 2, this is where we're replacing both. And for the pole, we're just replacing r with negative r. And I like to write that at the top too, just to remind myself of what I'm doing, especially when I'm first learning something. All right, so let's plug in. R equals 2 sine of 3 times negative theta. So here we start our cleanup process. This argument becomes negative 3 theta. Now we want to use our negative angle identity for sine. Remember that sine of negative theta is equal to negative sine of theta. So this negative is going to come out of the argument, and in front of our sine, r equals negative 2 sine of 3 theta. There's not really any other cleanup to do, so we compare it to the original. It is not the original, so it fails the test. So it may or may not have this symmetry. We don't know for sure, but it's not going to help us in our graphing process. Next, we're testing for symmetry with respect to the line theta equals pi over 2. We're going to replace both theta and r with its opposite. So this will be negative 3 theta. We'll use our negative angle identity again and take the negative out of the argument of the sine and put it out in front. We look to see if there's any more simplifying to do. Well, we could divide both sides by negative 1. That's frequently helpful when testing for symmetry. It's going to be positive r and then positive 2 sine of 3 theta. Comparing it to our original, it is. So the graph of this equation will display symmetry with respect to the line theta equals pi over 2. So that right there, when we go to graph, is going to cut our work in half. Because if we know, remember that theta equals pi over 2 coincides with the y-axis, if we know that we have that left and right symmetry there, we're only going to have to get half of the points because we'll just be able to flip it about the line theta equals pi over 2 to get the other half. So that's great. Let's test for the pole too. We're replacing r with negative r. There's no cleaning up to do on the right side. We could try dividing both sides by negative 1. That worked last time. But it doesn't work this time. This is a maybe. We might have diagonal symmetry, but it's not going to help us lessen our graphing process. Okay. Let's try the next one. Let's test our 3 symmetries on r squared equals 9 cosine of 2 theta. Let's start by making my table. I'm going to write above what replacements I'm supposed to make. And that'll also just help you remember them if you write them over and over again. All right, testing for polar axis symmetry. We're replacing theta with negative theta. Cleaning up that argument, we get r squared equals 9 cosine of negative 2 theta. We want to use our negative angle identity for cosine here. We use that a lot when we're testing for symmetry and polar. Recall that cosine of negative theta is equal to cosine of theta. So the negative in the argument kind of just disappears. Cosine of just 2 theta, we compare it to the original. It is, the graph of this equation displays symmetry with respect to the polar axis, which coincides with the x-axis. So it's top and bottom. Right there, our work's going to be cut in half when we go to graph. Let's check theta equals pi over 2. Here we're replacing both with the opposite. So that's negative r squared equals 9 times cosine of negative 2 theta. Negative r squared is just positive r squared, and we want to use our negative angle identity on the right side again. You know that's going to be positive 9 cosine of 2 theta. We check back to the original. It is the original, so this is also going to display symmetry with respect to the line theta equals pi over 2. So it's up and down and side to side. Lastly, we're checking for symmetry with respect to the pole. We're replacing r with negative r. When we square that negative r, we get positive r squared equals 9 cosine of 2 theta. That's our original, so this also displays symmetry with respect to the pole. Graphing this one will be the least amount of work because we'll actually only have to do 1/4 of the circle, and then we'll be able to reflect our points side to side and up and down to get the rest of the circle.